how much force is required to make this turn. How much force is required to make that turn? So there's the car, and this is toward the center of the circle. So if we're looking right at the back of the car right here, what's acting on the car? What are the forces? I'll do that one last. It's on a surface, so I think there is a normal force, yeah, I've heard that one. Gravity, and that force is called weight. And then I heard friction. Which way does friction point? So we're looking at the back of the car, and it's going to turn like that. So, which way does friction go? Methinks friction is why that way? The car is doing this. What it really wants to do is going to basically the straight line. But it's not. It's going to go that way. Well, then there has to be something pushing it that way. There has to be a creator of that many newtons. This is just a number. Well, I think that's this. That is, if there's no stickiness between your tires and the road, you're not going to turn. You're just going to go in straight lines. Things that have no friction, that's what they do. They go exactly straight line. Like friction has got to be pointing towards the center of the circle. That right there is the creator of that many newtons. That's what's on the free body diagram. That's the physical force. This is just the size of it. That's just the size of it. I think that's what the free body diagram looks like. If something's going into a circle, you better have at least one arrow that points towards the middle of the circle that's not being balanced out by something else. Because we have a net acceleration here, right? If you have an acceleration, you have to have an unbalanced force. If there's nothing over here, there's just a force that way because the force is towards the center of the circle. There has to be something that points towards the center of the circle. If you turn off friction, that's what it does. No friction with the tires, it goes in a straight line. So there has to be something that's pushing it from that straight line always towards the center of the circle. That's the roughness with the road. So I think that is what is really causing this centripetal force in this case. That just gives you that number of newtons. So part B, where does this force come from? Yeah, friction. Friction is the cause of the centripetal force. So, well, it gets more interesting. It says mu sub s is 0.60. How large is the static friction force? I think this is what this question is getting at. It takes almost 4,000 newtons to go into the circle for that object. Now they're saying, okay, here's how much friction stickiness you've got. How big is the friction force? This is what you need to go into the circle. So how do I figure out the size of the friction force? The force of friction is a coefficient times the normal force. And they tell me that the coefficient is diagram and figure that out? Yep. It doesn't move up and down, so the arrow up and the arrow down should come out, to be the same size. I'll look at the forces up and down. It does not move that way, so there is no acceleration. Add them all up, I'll call the one going up positive, the one going the other direction is a minus sign. There's a 0 for acceleration. In this case and in this case only, the normal force is the object's weight. That's not always the case, but that's what I would put in over here. M times G. Mass. And I think I'll just use 10 for gravity. 1,000 times 10 is 10,000, and then I take 60% of 6,000 newtons. So this is 6,000 newtons. So friction can give me up to 6,000 newtons. To go into the circle, I need about 4,000. The car gonna do it? You have enough friction, right? You have enough friction. But there's enough stickiness with the tires to provide circular motion. So your tires are bald, right? That's a problem, right? Or suddenly you wake up and you live someplace that gets icy roads and so forth. Your tires might be good, but all of a sudden you're on a sheet of ice and the coefficients of friction change and so forth. And so the civil engineers can do something to help you when they know what is the top speed the car can have and still make the point. So I think when I take a look at part D, on a centripetal force, the number of newtons needed to go into a circle is given by this. But I've only got 6,000 that's available. So I think I'm going to use all of it. The mass of the car is not changing. But if I use all of my friction, that's going to tell me my maximum velocity. And this corner is 50 grams. Yeah, you use everything that's available to you. This should tell you exactly what that top speed can be. Now, the velocity here is the important quantity, I think, yeah, because it's squared. Changing speeds a little bit has a big effect on the calculations and so on. So I'm going to get 6,000, multiply both sides by 50, divide both sides by 1,000, and then take a square root. 17.3. Not that much different than 14 meters per second. In 14, it looked like they made it easily, right? So, I mean, this is about 4,000 newtons, and they have 6,000 available because of the stickiness of their tires with the road. But only increasing this by a few meters per second, suddenly they're approaching this because the V is squared. If you double the velocity, you need 4 times more newtons to go into the circle. Because V squared, and you have 2, you square it, you make that 4. So small increases in velocity are big deals. They're big deals. But I think the numbers that we saw up here look pretty good. When objects are going to go around the Earth and not crash into the Earth, you got to get them going 5 miles a second, which then means that you're going around the Earth every 89 minutes. So I think those are the true orbital velocities and so forth. So Newton knows 300 years ago what it means to go into orbit. And we'll see exactly how this is going to get worked out in our next lecture. But he's imagining the Earth being shaped like this. Does he really know 300 years ago the Earth was shaped like that? that way. It's been known for 2,000 years. Accurate to 2%. All you gotta do is put a stick in the sand and measure some shadows and stuff like that, and you can get the radius of the earth within a couple percent and so forth. So that's not a big deal. But Newton is imagining putting a cannon here on the earth, and if you shoot the cannon, the object does this. Nice, perfect parabola. Because no, shoot it faster. Shoot it faster. If you shoot it faster, what does it do? It goes further. No, you gotta shoot it faster. All right, shoot it faster. And it does that. It goes, no. You gotta shoot it at 8,000 meters per second. The cannon did not exist 300 years ago. It didn't exist until the 1950s. And that cannon is the rocket engine. So shoot it at 8,000 meters per second, and it does this. The projectile has this path, but the Earth has this shape. Is that object falling? Yes, it's falling. It's falling from the straight line that it wants to go in. It's falling from its inertial path, right? It's getting farther and farther and farther and farther from that straight line path. It's in free fall. But it's going so fast sideways that as it falls, the Earth is curved away from it. So it falls forever. It falls forever. It's forever falling. This is what we mean by object being in orbit. So this is what orbit is, that it forever falls from that straight line, but it matches the curvature of the Earth, and that magic number for the Earth is this launch speed here of something right around 8,000 meters per second. Anything less, the Earth gets in the way. So the astronauts are in free fall. They're falling from that straight line path. They're a projectile. It's just that they're going so fast sideways that the Earth conveniently gets out of the way. Now, I can have you go in free fall in an elevator, just cut the cable, now you're in free fall. The problem is the Earth gets in the way. So you can experience what they do, except you experience the crash at the end when, this thing is gonna fall forever. And it falls away from the straight line, and if it's falling from the straight line, there must be a force that's pushing it away from that line. So when it's like right here, it wants to do that. There must be a push away from that straight line. And when it's right here, it wants to do that. So there's a push away from that line. The push is always inwards. The push is inwards. I think the only thing that's pushing the capsule inwards is the gravity force of the Earth. Turn off gravity, off it goes the straight line. We don't know how to turn off gravity forces or anything like that, but if that's what would happen, yeah, then it follows its inertial path. So I think Newton is understanding this 300 years ago. So it's not a matter of not knowing the physics or understanding the physics, it's a matter of the technology existing to get to something like that. And mankind's going to probably be faced with those types of situations always. You can go to the whiteboards at a university, and your graduate students are building time machines on the board, and it's just that we don't have the technology to actually grab stars and move them around and put them in certain configurations. And if you fly your ship through those gravity fields, then your time is considerably different than somebody you left behind. So it's a time machine. So those things can be done on the board like Newton was doing 300 years ago. We're missing the technology to do that. It seems like, we'll never be able to grab a star and move it. Well, Newton probably thought, we're ever going to make a cannon that can go 8,000 meters per second? It might be hard for him to imagine that. But, sometimes our knowledge, outstrips the ability to make devices that can do those types of things. So there's a possibility. So, what do you take away from today? If you're going in a circle, you have to have a force. Objects do not go in circles on their own. They go in straight lines, naturally. You've got to force them from the straight line. which means that there has to be a net force pointing in towards the center of the circle. That force is caused by tensions in the string, friction, gravity, next semester electrical forces, maybe magnetic. It can be caused by any force to make you go into a circle. The generic term for all of those is the centripetal force, because it just calculates the number, but it doesn't tell you where it's coming from. So it's easy to calculate the number, but sometimes it's hard to figure out exactly from where that really kind of comes from. Our free body diagrams have to have something that points towards the center of the circle, otherwise you can't go in the circle. And usually the situation will tell us what that happens to be in terms of what force is creating the centripetal force and so forth. Next Monday, the force will be one and one only. That'll be the gravity force. So Newton, he starts off his career, he's about your age, he's 20 years old. He's at Cambridge University, and there's an outbreak of the bubonic plague, and which is interesting because there's a talk today about that downstairs right after this class. So everybody runs for the hills, and so he goes back home to the farm, and I guess that's where he's sitting in the apple orchard. He's watching apples fall or whatever. He's going to work on the gravity problem for about 20 years. So you guys get frustrated if you work on a problem for like 10 minutes and don't get the answer. He's working on this thing for 20 years. And he doesn't publish it, even though he kind of knows he thinks he's got it right. But that's not the way science is done. It's not, I think it's right. It's, do I have evidence that this is right? We need to have the experimental data and so forth. And he has experimental data that is old, that everybody knows about. That is, if he's going to start talking about the gravity force, you've got it in chapter 5. There's some talk, and I guess it's kind of traditional. It's the hardest problem that mankind had faced up until Newton's time. And that there's these 5 objects that you see in the night sky, and they do crazy things. So they're called the wanderers, the planetes. The planets. You can see 5 with your eyes. See Saturn, Jupiter, Mars, Venus, and Mercury. And they do very strange things. They don't follow the motion of the other objects. So if you get like a constellation, and you watch the stars, they stay together, and they move as a package. When you put a planet in there, it doesn't move with the package. It'll go with them for a few nights, and then it'll stop, and then it'll turn around and do just crazy things. And so you've got these objects that even the ancient Greeks knew were special. And people have been working on the motion of the planets for Aristotle, 23 centuries ago. Ptolemy, Nicholas Copernicus got pretty close in the 1400s. But eventually Kepler will come up with the right mathematics that gives you the actual motion of these objects. But he doesn't know why it works. He just says, we have the data, and here's my formulas, and it calculates their motion. But that's not really good enough, right? If you really understand something, it's like, well, what's causing this? And that's where Newton's going to say, yeah, I think it's the force of gravity. And he knows that it works for those objects. What he doesn't know, or what he really wants, is some new object, and that's the moon. And so he keeps keeping the guys at the Royal Observatory, like, make these measurements on the moon, make these measurements on the moon, because I got some predictions that my math is telling me, but I need some experimental data and so forth. So he's going to wait until they can publish data and so forth. Then he knows that the law of gravitation that he's going to produce is working for at least the objects that they can see and so forth. And that'll be a great testament